Okay, so in this video, we're going to continue our follow-up to our least squares regression and look at evaluating certain assumptions using residuals generated from the regression analysis. And what I actually kind of worked up was just a little bit of a cheat sheet, and a lot of the diagnostics I kind of there's a nice review of them at this particular site right here, so you can always go there and kind of get a nice review of how to generate various things using STATA. Anyway, I've kind of worked up a little cheat sheet that I've been kind of working from as I go through these videos. So the next issue that I want to cover is just the issue of identifying problems with multicollinearity among your predictors. So we've run our basic linear regression, back up here, and we looked at the scatter plots. It looked like there were no, nonlinear relationships between or among your predictors or the independent variables and between the independent and dependent variables within the model. We also just kind of generated a correlation matrix to kind of look at the relationships among the variables. And one of the assumptions in your regression model is that your predictors are not collinear, and what that means is that they're not so highly correlated with each other that they're redundant in terms of the information that they're going after in the dependent variable. And so, one way that you can evaluate that is to look at just a correlation matrix and then looking for correlations that fall, really kind of in the 0.8s or above. Obviously, if you're in the 0.7s, you're getting up there pretty highly, but nevertheless, it looks like visually, or looking at the correlation matrix, none of the correlations here were extremely high. And when I'm talking about the correlations, I'm talking mainly about the correlations among the predictor variables. So, it's really this part of the matrix that, this part of the matrix that I'm really kind of focusing in on, not so much the dependent variable. So, at any rate, so there's no real evidence there, but I can also follow up with another set of tests, which is looking at the variance inflation factor. And basically, what happens is that if you have high levels of collinearity among your predictor variables, then what that does is it kind of jacks up or increases the standard errors, and it's really you end up being less likely to find statistical significance for any of the given predictors. So what we look at is sort of the issue of the variance inflation, meaning, are the standard errors inflated, and is that, contributing to a problem with significance? So what can happen is that if you have a large number of predictor variables that are all, let's say this is a dependent variable, and let's say I've got a set of predictors, they're all highly correlated with each other, then they're not really going after unique sources of information. And so the end result is that the R square can indicate significance, but your predictors may not. And so we can ask for variance inflation factor statistics to kind of get an idea as to whether there's inflation in those standard errors. So to do this, then I can use the estat VIF command. So I'm going to type in estat VIF and then hit enter, and so there you go. And so conventional rule of thumb is you have greater problems of collinearity when you have a VIF value associated with a predictor greater than 10. And so you can see right here that none of the predictors have a VIF value greater than 10. So that's really kind of indicating that we're in pretty good shape, again, concerning the issue of collinearity. Keep in mind too that if you just look at the zero order correlations, that only gives you sort of an idea about whether any two variables are highly correlated, but it could be that one predictor is a linear function of a set of the other predictors, and so that's where the VI, evaluating the variance inflation factors can be helpful. You can kind of identify problems at that level. Okay, so moving on, let's look at the residuals plots. So basically, we have assumptions concerning the distribution of residuals. And so, just kind of as a maybe as a refresher or whatever, when we generate a regression model, we essentially are generating a line of best fit. And so I'll give you sort of a simple example. Let's say I'm just running a simple regression because I like to, it's a little simpler to do it this way. So if I was running a simple regression where I have one predictor variable and one dependent variable or criterion variable, I will have a plot of data points. And essentially the idea is that I'm generating a regression line that hopefully will fit the plot of those points. Okay, and what happens is that when I'm looking at the relationship, this line right here reflects predicted values on y. So these are the predicted values on y at each level on x. And so, the data points, essentially the difference between, let's say this is an actual score on y right here for one particular case, then if I go vertically up to this line right here, that would reflect the predicted score on y. So let's say this is person 2 in my data set. This would be person 2's actual score on y and person 2's predicted score. And the difference between those two is called, is basically prediction error. And it's also referred to as a residual. And so the idea is that in linear regression, the residuals should sum to 0. So I'll just say the sum of the residuals should will equal 0. And what we're looking for is that the residuals exhibit a normal distribution. Technically, it's really conditional normal distribution. So if you think about it, at each level on x, if I could draw sort of a distribution of residuals around the regression line, they should exhibit normality. And then also, if I compute the variances, I'll just use sample notation here. So the variances of the residuals at each level, the idea is that they ought to exhibit constant variance. So in other words, the residuals should exhibit conditionally normal distributions and exhibit the same variance across levels of x. So those are, some basic assumptions related to the regression model. And what we need to do then is to evaluate how well those assumptions are met. And so that's where the use of residuals plots comes into play. So in order to work with the residuals plots, there are some options through the the menu option down here. If you go to linear models, you'll see it's got regression diagnostics, and you've got some residual plot options and so forth. But I'm going to actually focus mainly on using syntax, and as we go through the kind of my little walkthrough, I've already kind of denoted what exactly I'm going to be seeking. And so the first step is that we need to generate a variable that captures the predicted values on y. So it's those fitted values, which is actually kind of comprising the regression line. Then I'm going to generate a new variable that represents the unstandardized residuals. So in other words, the prediction errors in their original raw score metric, but the unstandardized residuals essentially are going to be centered at 0. So in other words, you'll have positive residuals, negative residuals, and if you sum them up, they should sum to 0. And like I said, and we're making the assumption that the residuals are normally distributed and have a constant variance. So I'm going to generate the unstandardized residuals using the predict command. I'm also going to ask for standardized and studentized residuals, and in particular, these two can be pretty handy in terms of identifying potential outliers. So at any rate, in terms of the commands, you'll notice that I've got predict y hat, and basically this is essentially the name of a variable that I'm creating to reflect those fitted values on y. So at any rate, what I'm going to do is I'm going to go in here and I'm going to type in predict, and then I'm just going to call it y hat. So the default use of the predict command is actually going to generate the fitted values. So I'm just saying, give me, I'm just saying name that variable y hat. So I'm going to hit enter, and you'll see it says option XB assumed fitted values. And so over here, you can see it says y hat, and a little bit further over you can see it says fitted values. It's a little hard to see over here, but that's what it is, the fitted values. So at any rate, so let's see if I can, okay. So now I've got a new variable in my data set. So I'll just go to browse, and you can see it says y hat. So those are the fitted values. Okay, so now what I want to do is I want to generate another variable for unstandardized residuals. So you'll see that I've got UR comma resid. And basically this is the name of a new variable. So this can be any name that you want. So I was not being particularly descriptive, but I could have called it R or whatever. I could call it whatever I want to call it. This is the main part, though, of the command that says generate the unstandardized residuals. So I'm going to go in here and I'm going to type in predict UR, and then I'm going to say RESID. And then when I hit enter, you'll see it says residuals over here. And so that's the new variable in my data set that contains those unstandardized residuals. So if I kind of scroll over here, you can see there it is. Now if I want the standardized residuals, then I have to use the rstandard subcommand, and so the new variable I'm creating is SR. So I'm just going to type in predict SR, comma, and then use the command. So I'm going to type in rstandard, and now you can see that it says standardized residuals over here. This is the new variable in the data set. And then I'm going to create the studentized residuals as well. So I'm going to use predict, and I'm just going to call it R for studentized. I could call it whatever. And then I'm going to use the subcommand R student. And so now you can see over here, these are the studentized residuals. So that's that one right there. So next, if I want to look for assessing the question of whether or not the constant variance assumption is met, or homogeneity of variances, there are a couple ways that you can do this. There are test statistics similar to Levine's test with analysis of variance, which in this context, in the regression context, we would be using something like the Broich-Pagan or White's test for constant variances. And then there's also a visual inspection as well, and so we can use the residuals plots in order to assess whether or not that assumption is met. So one way that we could look at this is by using essentially what I like to do is I'll type in two-way scatter, and then what I'm going to do is I'm going to go ahead and plot the studentized residuals against the y hat. So you can actually plot the unstandardized or standardized residuals, but I'm going to just go ahead and plot the studentized residuals against the fitted values. So I'm going to type two-way and scatter. So these are the main portions of the command. And then I'm going to type in the y variable, the variable that's going to be on the y-axis first. So I'm going to type in R for the residuals, studentized residuals, and then I'm going to type in the variable that's going to go onto the x-axis. So I'm going to use y hat y hat here, and then comma. Now, I like to generate sort of a fit line, if you will, basically centered at 0, or reference line is centered at 0, in order to kind of study the residuals to see if there's any kind of trending in the residuals, or kind of just kind of visualize what's going on. So it's helpful if you use the Y line option, and I'm going to type in 0 because I basically want the reference line in relation to the centered residuals. So when I do that and hit enter, you'll see that now I have, this is the reference line I was telling you about. And so we've got the fitted values on Y plotted on along the x-axis, and the studentized residuals on the y-axis. And so what we're looking for several things. First of all, we're looking to see if the residuals kind of exhibit a random display. And so are they randomly distributed around this reference line right here? And to the extent to which they look like they're randomly displayed, that's actually a good thing. That means that we're not observing any kind of nonlinear relationships or any kind of unspecified predictors. Where there's some different functional relationships between the predictors and your dependent variables. So it looks like overall there's a fairly random display, and there's no kind of evidence of any kind of non-constant variation in those residuals. So, and what I mean by that is that if we're talking about the issue of constant variance assumption, what we're basically saying is that what we would expect is if there's a violation of that assumption, if these are the fitted Y values, and these are the residuals plotted in relation to those fitted values, what can happen is that your residuals, they could exhibit sort of this kind of patterning where essentially, as you're looking at them, they're kind of exhibiting a fan-shaped pattern. So they're kind of spreading out. And what that basically means is that the model's doing a much better job of predicting the values on Y at lower levels of the fitted values, whereas as the fitted values are increasing, the model's doing an increasingly worse job of predicting Y. So in other words, what we want is the prediction errors to be fairly constant, or to be constant across levels of your fitted values on Y. Additionally, we can plot against each of the predictors. So, for instance, let's say that we exhibited, we see a sort of a fan-shaped pattern emerge in the data, and where we're plotting the residuals against the fitted values. We might then go back and look at each of the individual predictors to see if there's a particular type of fanning on a given predictor. So the residuals plots can be really handy in that respect. So that's one way that we can kind of visualize, kind of get a visual idea as to whether or not there might be some problems with meeting the constant variance assumption. Also, another possibility is with the residuals plots is that in addition to kind of visualizing whether or not there might be some violations with constant variance, we can also look to see, how the residuals, do they exhibit any kind of nonlinear patterns. So in other words, if these are the residuals plotted against, the fitted Y or any given X, it's possible that the residuals might kind of exhibit sort of a nonlinear trending when plotted against the fitted Y's or the actual. So if you get sort of a curvature in those residuals, then what that really is kind of signaling is the possibility that you have that the relationship between one or more of your predictors and your dependent measure is not linear. That basically maybe some other trending or perhaps an interaction effect is going unmodeled. So in other words, you would have a specification error, and so that might be yielding sort of a curvature in terms of the residuals. So the residuals plot can be really handy just kind of in visualizing you know, whether or not you might have kind of a violation of non-constant variance, or potentially sort of a specification error as a result of not correctly modeling the functional relationship between your predictors and your you know, your dependent measure. So in this case, there's none of that. Also, another possibility is that with the studentized residuals, you also you know, you can look at the plot and you know, basically you know, there are various rules of thumb, but you know, with the studentized residuals or the standardized, the studentized residuals is a little bit more sensitive to doing this, but it's also handy in terms of identifying potential outliers in your data set. So for instance, you know, it might be that in general, let's say I'm looking at the relationship between two variables, and let's say you know, the data kind of exhibits this type of trending. But let's say I have, you know, an outlier in the data. You know, without that outlier, the relationship might look like this, but then with it, you know, it might look more like this. And so you can actually utilize, you know, the standardized residuals and studentized residuals to identify potential outliers that might be impacting your regression model. And so, you know, looking at the studentized residuals plotted against the fitted values right here, what we're looking for, in general, we're looking for observations that deviate. In general, what we're looking for are residuals that fall between a -2 and a +2. Okay, so basically we're kind of looking for residuals to fall within this range right here. Okay, and so any observations that are kind of falling outside of that might be potential outliers. So you can see right here, we got a potential one here and a potential one here. And so we might want to study those observations a little bit more closely in order to identify, you know, whether or not these are problematic cases, and then maybe take some kind of come up with some kind of strategy for dealing with those. So at any rate, that's kind of an example of using the residuals plot. Another possible plot that we could utilize to further examine whether or not there might be problems with the non-constant variance assumption is to take the unstandardized residuals and square them, and then plot the square of those residuals against the fitted values. So what I'll do is I'll kind of show you that you know, our original unstandardized residuals was the variable we just called UR, and essentially I'm going to use this equation right here, and I'm basically using the generate command to generate a new variable that you can see right here. The new variable name is SQUR, and then I'm going to say equals, and then I've got the name of the original variable, and then the caret, and then 2 to square it. So basically, I'm just going to kind of move that over here. So it's just generate the name of the new variable that's going to appear in the data set over here, and then equals, and then the name of the original variable, and then square it. So when I hit enter, you'll see that now when I kind of scroll down here, you can see there it is right here. So this is the squared unstandardized residuals, and I'm going to plot those against the fitted values. So what I'll do is I will type in two-way scatter SQUR y hat, and I'm not going to add the reference line at 0 because essentially 0 is this, you know, it is possible to have observations where the residual is 0. So basically you'll see, oops, oh, I think I misspelled it here, so I'm just going to copy that there again. I meant to say SQUR, there it is. And so there's the plot, and so you can see, you know, the prediction errors can't be, you know, if I square the prediction errors, then I can't have any negative values. And so, really what we're looking for, again, is sort of a fanning type of pattern. There's not really a consistent fanning, but there are a couple of observations right here that's a little bit perhaps interesting in terms of potentially having an impact on the solution. But really what we're looking for is something where essentially you've got sort of a fanning, a consistent fanning pattern where it kind of looks like this. It doesn't look quite that way. It looks, for the most part, you've got some residuals that are clearly larger than others, but there's no real consistent pattern. But you do have, like I said, you have this observation might be potentially interesting to look at. So at any rate, that is the use of the residuals plots and the plot of the squared residuals in looking for potential, looking at the constant variance assumption and looking at possible outliers and possible nonlinearity between your predictors and your dependent measure. If you want to further kind of look to see the nature of any kind of outliers, another possible approach is, you can essentially, because the studentized residuals are either positive or negative, what we might want to do is to essentially find a quick way of identifying potential outliers. And so, as I said, what we're really looking for are cases that would be where you'd have a studentized residual that are greater than positive 2 and or less than negative 2. And this is one potential threshold, and basically our worries kind of increase, when the studentized residuals, exceed 2.5 or 3, and or are less than negative 2.5 or 3. So, there are various rules of thumb. We're basically adopting a fairly liberal standard for identifying a case as an outlier. If we stick with this one right here, a little bit more conservative standards utilize the 2.5 or 3. The quickest way that we can kind of identify which cases might have the largest studentized residuals is we can essentially generate a new variable in the data set. And so you can see right here that it says generate. So using that same idea as before, we had generate the name of the new variable equals, and then some statement about computing that new variable. So we've got generate, and this is just an arbitrary name that I'm using. I'm just saying basically the absolute value for the studentized residuals. So I'm essentially, I like to just copy and paste in here. So I'm just going to copy and paste that in here. And so, like I said, I'm generating a new variable, which is the absolute value of the studentized residuals, which was, basically what we had previously. And really, let's see, absolute value should say R. Okay, so now I've generated the absolute value of the studentized residuals. So, so yeah, basically in this description right here, it was a little bit off. It should have said absolute value of R. So I'm going to save that there. Okay, so there you go. So now I've got this new variable in here. And so now what I can do is I can sort on that variable. So I'm going to type in sort and then on this new variable that's been created, which is the absolute value. So I'm going to say ABSVRSTU. And then, so I've sorted on that variable, and now I can type in list. And I want the studentized residuals and these IDs for the cases in the data set, because I want to identify which cases are exhibiting the largest studentized residuals. So just kind of going back in, you can see I've got the student ID, and then I've now sorted on this variable right here. So these are the IDs. So actually I can scroll down. You can kind of see right here, this is the student that had the largest ID, or the largest absolute studentized residual was student number 12. But if I didn't want to kind of do that in that kind of way, I can just say list ID ID, and then just basically say R and hit enter, and so there it is. And so that's just the list. And so basically the studentized residuals have all been sorted in an ascending fashion, and so then I can go to the bottom. If I want to do this a little bit quicker, then what I could do is I could say list ID R, and then I could say N, and then just identify, since they're sorted in, oh, excuse me, that was wrong. That was the actual studentized residual. I wanted to list on the absolute value. So you got to make sure your syntax is right, or else you can kind of end up with messing up. So I'm going to say list ID ABS V R STU, and again, that's listed relative to the absolute value of those residuals. And so again, is student 12 down here with the largest, followed by student number with the ID of 7. That was the absolute value of the residual for that student. But if I wanted to kind of, instead of sorting in that kind of way, or being that specific, I could say ID, and then I could say ABS VRSTU N, and then if I would just want to list the last 10, I could have just done that, and there you go. So you can see that the absolute values for these are the absolute values for the largest 10 studentized residuals. And so you can see again, there's student 12 with the largest value, student 7 next largest, and so forth. So those are just a few, I guess you could say, a few tricks of the trade that can kind of be helpful in identifying potential outliers.